So that video that we just watched is based all around that slide, where they go down the slide, they come off at a 30-degree angle, okay, going about 20 meters per second. How far do they fly? Okay, that's the kind of thing that we're going to be able to calculate, okay, by the end of the day today, because we're going to look at angled projectiles and how they work in today's class. All right. So one of the best places to see good examples of this, okay, is in kind of old movies or old TV shows where they actually used practical effects, okay, for things like jumping cars over stuff, car chases and things like that. Because back in the day we didn't have CG, okay? The only way to make it look like a car jumped over a river was to jump a car over a river, okay? And that meant that you had to do a lot of planning, because also at that time, remote control technology wasn't as reliable or as good, and you actually had a stunt driver in the car, okay? You ever meet a stunt driver? Ask him to give you a thumbs up. That thumb will be like horribly crooked, okay? Any stunt driver who accidentally holds the steering wheel like we normally do during a jump will break their thumbs, okay? Because when they impact the ground, their fingers will go forward and the thumbs will get dislocated or broken, okay, in a backward direction. So stunt drivers are supposed to hold the steering wheel like this with their thumb on top, okay? So that doesn't happen, okay? Then they just break their wrist or something, okay? So it's a pretty violent thing to do, okay, to actually be in the car when it is jumped. And some of the jumps that were done, okay, were crazy. In fact, a few of them could not have a stunt driver. It just would not have been survivable, basically, given the length of some of the jumps that have to be done, okay? So what we're going to look at is probably one of the best shows ever, okay? Especially when it came to car chases and jumping cars over things. That would be the Dukes of Hazzard, okay? Which is kind of like, you know, humble little show from back in the late 70s, early 80s. Not the travesty of a movie they made about 10 years ago, because that was just a show, okay? But the actual television show, okay, from way back when, where there was a car or 3 or 4 destroyed every single show in order to show all of the jumps that they would do. In fact, over the course of the show's 7 or 8 seasons, they destroyed hundreds of beautiful 69 Dodge Chargers, okay? To the point where in the latter parts of the show, they could not get Chargers anymore, and they were actually jumping other cars that had similar bodywork from different angles in order to make it look like they were still jumping the original car. Okay? You can actually see in some of the ones I'll show you here, some of the jumps, that they're actually using a car they've already jumped. Okay? If you catch it at just the right angle, you can see that the hood is like roped down so it'll stay down, or the frame is already bent and twisted, stuff like that. You can actually see that in some of the shots because they just ran out of cars. Okay? Budget wasn't there or whatever. All right, so I'm going to show you a few of the jumps, and then we're going to have a look at one particular jump. In fact, it was the first jump they ever made in the show, okay, where they generally jumped across this pretty wide river. Okay, so we'll have a look at that. Okay, so here's the example we're going to look at. I'll have you guys write this one down so you've got a solved example of a projected at an angle projectile here. So in the video clip, we have the General Lee jumping the riverbed. Here's the information that we know. The General Lee is traveling at a speed of 32 meters per second when it leaves the ramp, and the ramp is angled at 20 degrees. So the General Lee is going between 120 and 130 kilometers per hour, okay, when it hits the ramp. Okay, so that ramp is angled at 20 degrees, and we are moving at 32 meters per second. Now, obviously, the General Lee follows an arc like it did in every single one of the jumps that we watched, okay, until it encounters the ground on the other side of the river. We're going to make one assumption here, and that is that the takeoff and landing points are level. Okay, that is that they are at the same height. There's no change in height between takeoff and landing. So this is all the information I have. I want to be able to calculate the horizontal distance that the General Lee flies. In other words, how wide is the riverbed? Okay, that's what I want to find out. All the projectile motion problems that we've done, we broke up into the 2 components, the vertical component and the horizontal component. these are no different, okay? There's still 2 dimensions to this motion. So what we have to figure out is, what do we know about each one of those dimensions? Okay? So from a vertical perspective, right now, without doing any calculating, for this whole flight, what do I know? What causes the general E to do that? Gravity. Okay. I'm going to make gravity negative on this one for this reason. At the beginning of this, the general E is moving upwards. At the end of it, it's moving downwards. Okay, so we do have a change in direction, and so our vectors have to be applied here. Okay, we didn't have to worry about that with the ones that went off horizontally because they were only going to go downwards. All right. Right now, I only know one other thing. Over the entire trip here, the vertical displacement is 0. The vertical displacement, obviously, is 0, not the horizontal displacement. That's what we're looking for. Okay. In order to get anything else, I need to do some calculating. That calculating is simply finding the vector components of the general E's launch speed, or sorry, launch velocity. Okay, it is being launched at 32 meters per second, 20 degrees above the horizontal, which means when it leaves the ramp, it has a horizontal component, which we will call V horizontal. Okay, that number will not change. It will travel at that velocity horizontally for the entire trip. And then it has a vertical component, okay, or its Y component, that will represent its initial vertical velocity. That is how fast it was moving upwards when it left the ramp. Okay? Neither of these numbers is 32. That's the most common mistake I see. I put 32 on here and people go 32, 32. No, 32 is at 20 degrees. We are looking for the horizontal component of that, or X component, just like in vector addition, okay, and the vertical or Y component, just like in vector addition. So how will I find the Y component? How will I find VI here? What trig function am I going to use for that? Sine, yeah, it's opposite the 20-degree angle. So VI is in this question, and in all projected at an angle questions, the sine of whatever angle we have, in this case 20, times the projected velocity, 32. All right, so when it leaves the ground, the general E is moving at 10.94 meters per second upwards, okay, from just a vertical perspective, okay? So I'm going to say that's positive because I made the acceleration, which is down, negative. Everybody okay with that? All right. Because the displacement is 0, that means that the object goes up and comes back down to the same height. Yesterday we were talking about that, and we said that if something goes up to a certain height and then falls the same height back down, its speed when it comes back down is equal, right, to the speed it went up at. That is true here as well. Okay, what goes up must come down. If it comes back down to the same height, its speed is the same on the way down as it was when it left. It has to be because it accelerated at the same rate over the same distance. Okay, everything is the same, so it has to come back at the same speed. So that means that VF is negative 10.94 meters per second. Okay, that's only true if the displacement is 0. If the displacement is not 0, you can use an acceleration formula to calculate what VF would be because you would know the displacement. Okay, and you'd be able to use one of our formulas because we always know acceleration is always 9.81. All right, I also need to calculate my horizontal velocity, okay, which is the adjacent side. So V horizontal is going to be the cos of 20 degrees times the projected velocity, 32 meters per second. whoops, not 32 equals 20 times 32. Okay, so horizontally, the general E is moving at 30.07 meters per second. Okay, the question wants me to find out how far horizontally the general E travels. What do I need if I'm going to calculate that? Time. Yeah. Okay, remember that your horizontal is always governed by v equals d over t. Okay, your vertical is whatever acceleration formula you need. Okay, so right now I have A, I have VI, I have VF, and I have D. Do I have some choices here for what formula I can use to calculate time? Okay, I think my best bet though is to use this one. That way I'm not using 0 as one of my givens. Okay, I can solve for time using real numbers. Okay. So time is going to equal then VF minus VI over A. Okay, and for us that's going to be negative 10.94 minus 10.94 over negative 9.81. Okay, that'll give us the flight time of the general E through this jump. Okay, so 10.944,644,59. I'm just going to multiply it by 2. Okay, because negative 10.94 minus 10.94 is basically 2 times 10.94. Everybody okay with it? Yeah. All right. Then I'm going to divide that by the acceleration. And I know I didn't make them negative, but I didn't make either one of them negative, so it's going to work out. Okay? All right. The general E is in the air for 2.2 seconds. Okay? So they're yelling, "Yeehaw!" all the way across for 2.2 seconds. You didn't know that. That's what they yell and they jump. General E. Okay? It's awesome. That's awesome. Okay? All right. So we got 2.2 seconds as our time here. Obviously, we want to keep all the decimals. I'm just rounding off to save time here. All right, now can I calculate my horizontal displacement? Okay. So D equals V times T. That'll be our 30.07 that we calculated before times 2.2. Is this very much like what we did with the horizontal ones? Yes. Yeah, it is. I mean, we didn't have to do this part for the horizontal ones because VI vertical was 0. Okay, in this case we have to do a little bit of trig and then we're off. Okay, so we're going to take our time, our 2.2, multiply it by our 30, well, not 10, 30.07016387. Okay, it's 67 meters across the river. Okay, give you an idea, one of the straight sides of the track out there is 100 meters. That's 2/3 of it. Okay, they jump 2/3 of one of the straight sides of our running track. Okay, impressive. So 67 meters is the horizontal distance across the riverbed. Everybody with me there? All right. There's one other thing that one of these questions might ask you. And it might ask you to calculate the maximum height that the car reaches above its launching point. All of our givens remain the same. This value that we calculated here remains the same. Only one value changes, and that's VF. What is your vertical velocity at your highest point? 0. Okay, remember, if I throw this marker up in the air, at its highest point is where it's instantaneously stopped, turning around and beginning to fall back down. Okay, everybody understands that? Okay, so the only thing that changes is that at your maximum height, VF equals 0 meters per second. So I have A, I have VI, because I've calculated it already, okay, and I have VF. And I'm looking for my height, which is my vertical displacement. So I'm looking for D. I have VF, I have VI, and I have A. Okay? I also have the time, but I have to be careful if I use the time. The time I calculated was from launch to landing. where am I at the maximum height in terms of time? Halfway. Okay? That's why I very rarely encourage anyone to use time when they're calculating the maximum height. Inevitably, people use the whole time. Okay? And if they do that, they're not going to get the right answer. Okay? Because they're using twice as much time as actually occurred. Right? So I generally just go with, I have VF, I know it's 0. I have VI, I calculated it already. I know A is negative 9.81, and I'm looking for D. What formula can I use to get D? We didn't use this one very much back during acceleration, but you use it every time you're calculating maximum height because it's the most reliable one. Okay. All right, if I'm going to manipulate this for D, I'm going to subtract VI squared over to the other side and then divide by 2A. So I'll have VF squared minus VI squared over 2A, and that'll give me my maximum height. Okay. So when I plug in those numbers, 0 squared minus 10.94 squared divided by 2 times 9.81. Okay, and I've got my 10.94. All right, so 0 minus 10.94464 squared. Okay, divided by 2 times 9.81, 19.62. Oh, and I forgot to make that negative, so that's my bad. That should have been negative. Okay, so generally reaches a height of 6.1 meters above the ground. To give you an idea, this ceiling is around 3 meters above the ground. Okay, the gym is around like 12, 13. Okay. So 6 meters is pretty high. It's 20 feet. Okay? So generally is going to fall from a height of 20 feet. Okay? When it crashes into the ground. In addition to the fact that it's moving very fast horizontally. Okay? It's also moving very fast vertically when it hits the ground on the other side. Okay? All right. That's sort of making sense. Basically, every projectile motion question is going to involve doing the same things. Okay? Finding VI. Knowing what VF is going to be, it's going to be the same most of the time. Okay, knowing that V horizontal is the adjacent side. Okay, looking for all of those things. All right, so we've got a few minutes left here. I want to show you one more clip. Okay, for this.